question 2. A stub shaft of 85.2 millimeters in diameter must be cooled or shrank to a diameter of 85 millimeters in order to insert into a housing. So we're being tasked to calculate by how much does the temperature need to be to cause the shaft to shrink by 0.2 millimeters in diameter. And here we're being tasked to assume that the coefficient of linear expansion is at 12 times 10 to the power minus 6 per Kelvin. And the expected result after we work through this problem should be minus 195.6 Kelvin. So let's look at problem 2. So this is a diagrammatic representation of the problem. So we've got this stab shaft which measures a diameter of 85.2 millimeters. And we're being tasked to find out how much does the temperature need to be to cause excessive contraction of the shaft for it to shrink from 85.2 to 85 in order to fit into the bore of the given housing. So that's essentially the task, the challenge that we need to.
Alright folks, let's look at this problem in much more detail. So you have a situation whereby a shaft of 85.2 millimeters needs to be fitted into a housing which has a bore of 85 millimeters. Now if we're looking at the diameters, we realise that the shaft is slightly larger than that of the bore in the housing, which means that for this operation to take place, this can be done in two ways. Either the housing needs to be heated for the bore to expand enough to accommodate the shaft, or the shaft is cooled for the diameter to contract to fit into the housing. So whatever is economical. So I think in this instance we're going to look at how the shaft can be shrank significant enough to fit into the bore of the housing. In the problem given some information to help us work this out. So the linear coefficient of expansion, so that's characterized by alpha, is given as 12 times 10 to the power minus 6 per Kelvin. Okay, centigrade can do it that way, but I'll do it per Kelvin. Okay, so we've got that. So to look at the change in length, but in this context we're looking at the change in the diametric span. So change in diameter, so let's call that delta B, will be equal to original diameter of the shaft multiplied by the coefficient of expansion times the temperature differential. So let's call that equation 1. So since we're interested in temperature differential, if we decide to transpose equation 1 by making delta T the subject, then the temperature differential, so the change in temperature, delta T will be equal to delta D divided by alpha times the original diameter. Equation 2. It's fairly straightforward. Okay. So we know what alpha is, so alpha has been given. We know what the original diameter of the shaft is, so that is 85.2. And the change in diameter will be the difference between the diameter of the housing, which would be the final diameter, because we want to shrink the shaft to be at least equal to that of the housing. So that becomes a full transition. Okay, so very little pressure required to knock it into place. So we've got that. Okay, so let's do it that way. And it's very important that we do this in such a way that we get an answer that characterizes shrinkage. So change in diameter so that is delta B will be equal to the final diameter, which would be the shrink diametric span of the shaft, minus the alpha original. So that'll be 85 minus 85.2, and this will give us 0.2 millimeters. Now if you want to convert your length from millimeters into meters, it is up to you. Alright? But the most important variable here is the change in temperature. So now that we've worked that out, we can then use equation 2 to figure out what the temperature differential is. So the temperature differential will be equal to, well, that'll be minus 0.2, that'll be minus 0.2 all divided by 12 times 10 to the power minus 6 times 85.2. And our result will be in Kelvin. So the final part is to do the linear computation to work out our final result. So this will be, this will be minus 0.2 divided by into bracket 12 times 10 to the power minus 6 times 85.2, bracket close, and that will give minus 195.62 Kelvin, which will be the same as minus, if we add 5.62 plus 273.5, so that is approximately 468.8 degrees C, so if we're looking at the equivalent. And there we have it. Now alternatively, my preference would be to work this out in the basis of the aerial span, so the cross-sectional area. So again, it's more or less up to you how you want to go about working through this problem. So alternatively, we can do this. We can calculate this on the basis of the aerial span. To do this, the aerial coefficient of expansion, so let's call this alpha A, is approximately equal to twice the linear coefficient. Okay? So therefore, alpha A is approximately equal to 2 times 12 times 10 to the power minus 6. Okay, per Kelvin. So this is equal to 24 times 10 to the power minus 6 per Kelvin. Okay, so we've done that part. The next part is to calculate the original diameter, the aerial span for the original diameter with respect to the original diameter. So the original diameter, so let's call this original area, okay, with respect to the original diameter, so let's call this A naught, that will be equal to pi over 4 times E naught squared. Yeah, this will be equal to pi over 4 times into bracket 85.2 squared. So let's bring our handy calculator. So we've got pi over 4 times 85.2 squared. And that gives 5,701.24 millimeters squared. So we've got that. The next part is to calculate the change in area. Let's do that. So, change in area. Let's call that delta A. We will do pi over 4 times df squared minus d naught squared. Okay. So similar to what we did previously, pi over 4 times df squared, so that will be 85 squared minus 85.2 squared. Okay. So let's bring our handy calculator. So this would be 85 squared minus 85.2 squared times into bracket pi over 4. And that will be minus 26.7, let's call that 74 millimeters squared. Okay. So I'm going to use a similar methodology in establishing how we need to go about calculating the temperature differential. So since delta A is equal to the original area of the shaft times alpha A times delta T, then temperature differential that is delta T will be equal to delta A all divided by the original area times alpha A. Right? I tend to do this so that at least we've got a basis to verify or validate our final result. So let's do the new computation. So delta T is equal to the sectional area, the change in area, so that was minus 26 0.74. Okay, so let's not forget that's what we calculated previously. All divided by the original area, so that is 5701.24 times the area coefficient of expansion, which is approximately 24 times 10 to the power minus 6. Okay. And we want our units to be in Kelvin. Okay. So let's bring our handy calculator. So we've got minus, and use the fraction function. So we've got minus 26.474 over into bracket 5701.24 times 24 to the power minus 6. Okay, and that would be minus 195.43. Okay. So based on what we have, I mean the variance is very little. So to be very honest, we're looking at heated component. Okay, so this will more or less be a minimum, and the maximum will be 195.6. Okay, so at least this gives me some confidence in the result that we have. So again, there's two ways going about it. As long as the percentage variance is 5% or less, that's acceptable. Right? And there we have it.
So let's look at a summary of the problem that we just worked out. So to start off with, as I more or less stated, always note down the data that's been provided in the question. Then once you've done that, it's also good practice to have a visual representation of the problem to make it easy to understand what you need to solve for. So the circular diameter, the initial diameter, so that's given in the problem as 85.2 millimeters. The final shaft diameter, once it's shrank, will be 85 millimeters. So the change in diameter is approximately 0.2. So that'll be the difference in the two. And we've been given the coefficient of linear expansion for the material alpha to be 12 times 10 to the power minus 6 per Kelvin. So since the change in diameter delta D is equal to the change in temperature times the initial diameter of the shaft times alpha, which is the linear expansion coefficient, then the temperature differential delta T will be equal to delta D, so that is the difference in the diameter, divided by the product of alpha and the initial diameter. So we substitute all the known variables into the equation, do the needed computation, we get approximately 195.62 Kelvin. Okay. So let's try to predict the temperature differential using the cross-sectional area of the shaft. So we first off calculate the original cross-sectional area of the shaft. So that's simply pi over 4 times di squared. So that is the initial diameter of the shaft. So the original diameter, so the initial diameter is given as 85.2 or 0.0852. So put in the known values and we get the original cross-sectional area of the shaft to be 5.7012 times 10 to the power minus 3 meters squared. So we can then proceed to calculate the sectional change of the shaft when shrank for assembly. So delta A represents the sectional change in the area of the shaft, equal to pi over 4 times into bracket the initial diameter squared minus the final diameter squared. So once we substitute these values into the equation, we get a result of minus 2.674 or 735 times 10 to the power minus 5 meters squared. The negative sign is just basically showing a reduction in area. So for the area expansion coefficient, that is normally double that of the linear coefficient of expansion. So since we're given the linear expansion coefficient to be 12 times 10 to the power minus 6 per Kelvin, the area coefficient will just be twice of that, thus 24 times 10 to the power minus 6 per Kelvin. So since the change in area, delta L, delta A, sorry, is equal to delta T, so that's the temperature differential, times the original area of the shaft times alpha subscript A, so that's characterizing the coefficient of areal expansion. Then making the temperature differential the subject of this expression would be delta T is equal to delta A divided by the product of alpha subscript A times the original area. So just a question of substituting known values, and that gives a result of minus 195.4 Kelvin. So relating this with respect to working out via the diameter, we get a variance of 0.11%. So that's very, very close. Very, very close. So hi folks, there we have it. Alright folks, so hopefully everything made sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session. So please share and subscribe, and I'll catch you in the next section. Bye for now.